Hello, my name is Oliver Maiß, and I head the Research and Development Department here at ECOROLL AG. Today I would like to answer a question that we receive time and again, namely, can we replace a hardening process with deep rolling? And I'll just venture the bold thesis now. Yes, that is possible under certain conditions. What actually happens during hardening? During hardening, I want to bring about a targeted change in the microstructure to increase the resistance of my material. In the classic case, this happens by introducing temperature, adding carbon in the case of steel, and additional quenching after heating. So I heat my material, then the carbon has room to, so to speak, rearrange itself in the microstructure. Then I quench it. And yes, I create a tension in my microstructure and have thus achieved a higher strength and higher resistance of my microstructure. That is the classic case for hardening. That has enormous advantages. It is based on purely physical conditions that the material brings with it. It is very easy to control via the temperature. It can be achieved at very great depths. So components can sometimes be completely through hardened, which of course has enormous advantages. Hardness itself is defined as the resistance of a material to counteract the penetration of another material. And I'll claim now that in many cases this increase in hardness isn't even needed, but rather an increase in strength is achieved through the hardening. And this is what should be utilized. So through hardening, something actually happens. I also increase the static strength of my material. I increase the mechanical characteristic values of my material. And these characteristic values, I then use them in my design, in my dimensioning of my components. But this actual thing, what hardness really is, counteracting the penetration against a body, I often don't really want to achieve that through the increase in hardness. If I now compare classic hardening and simply point out the pros and cons, then one advantage is, of course, that the process is very well known. I can heat the component using a wide variety of methods. I can do it by laser, by flame, by induction, it doesn't matter at all. I can heat my component very well. I have the process very well under control. I can control it very well via the heat, and the process is of course also very scalable. I can simply build a huge furnace in which many components pass through over a long period of time. They are heated accordingly and at the end, so to speak, quenched. And then I have mass production. That is how many components are typically hardened in mass production. The disadvantage is clearly evident in this day and age. The high energy costs. To heat a material, a metal material, to heat steel, I need an enormous amount of energy. If we look at the carbon footprint and the energy costs of a component, of an entire component, then most of the costs and most of the carbon values are actually in the production of the material and in the heat treatment. So that means I have a very, very good lever there to bring these values down. In addition, we don't always just have hardening, but we usually also need an additional tempering. So my material, my component, has to be heated once more afterwards in order to remove stresses from the structure and make the whole thing a bit softer again. Because otherwise it would become very hard and very brittle. And I actually usually always need additional equipment. I need a furnace, I need an induction system, it doesn't matter, I need a laser system, I have to heat my component somehow and then quench it. Now, of course, there are many different methods for hardening a component. I can flame harden the component. I've simply listed them here and brought them along. No claim to completeness, just a few examples. I can flame harden it, I can carbonite it, I can plasma nitride it, I can nitride it, I can harden it with a laser. And I can also, I've brought this along too, if I really need this increase in hardness, such as with cutting tools, then I can additionally coat the component. This is also a type of hardness increase, which of course has no thermal effect, but which is also an additional process to create an increase in hardness on the surface. An alternative process is deep rolling. In deep rolling, a mechanical roller or a ball, some kind of rolling element, is pressed onto the surface of a component. And as it rolls there, it creates plastic deformation, reduces the surface roughness, introduces residual compressive stress, and, this is the crucial point here, also creates work hardening by increasing the dislocation density. And that leads to the hardness of my component being increased locally in the near surface area. And I can now, of course, use this effect to strengthen my component. And I can also use it to significantly increase the service life of my component. So I don't necessarily have to, and here's the point I want to make, I don't necessarily have to harden my component to increase its service life. I could try to be able to carry out this process, this deep rolling, simply after my machining on the same machine, and thus introduce residual compressive stress, introduce work hardening, and so increase the service life of my component. I can increase my hardness very locally within the near surface area. If I want to increase wear resistance, for example, abrasion resistance in the case of abrasive wear, I can also achieve through deep rolling. What I cannot achieve through deep rolling is a hardness increase from a soft steel to a very hardened steel. So I definitely won't achieve rolling bearing quality with a 100 chrome 6 if I simply deep roll it in its soft state. There are also materials where this work hardening effect is so small that you can't really detect any increase in hardness. That also happens. There are other materials, so-called trip or twip steels, which transform martensitically through heat or mechanical stress. If I then deep roll these trip steels, which transform mechanically, I naturally get an enormous hardness increase effect. But that's because it's a special material. The penetration depth is also different, of course. If I have a penetration depth of 1, 2, or 3 millimeters with induction hardening to a certain hardness value that's also relatively high, I can control that by simply adjusting my heating depth through the induction heating accordingly. And then, due to the physical effect, I simply get a transformation of the microstructure. With mechanical stress, the mechanical tension must act down to this depth. And that becomes difficult again with such high hardness penetration depths. So there are limits where it just doesn't work. And in many cases, I must honestly say, it's simply the case that we actually need this hardness increase at that depth. And then deep rolling is not an alternative. However, if you want to achieve pure hardening or a pure increase in service life, for example, in the area of fatigue strength, then I'd say just give it a try. Try to deep roll your component, see what the results are in terms of fatigue strength. Compare it with the hardened component, maybe it's enough. And then you've saved an enormous amount of cost. That brings me to the end of this video. I hope I was able to shed a little light on the subject. Regarding this frequently asked question, hardening or deep rolling, can I replace one with the other? I hope I was able to provide some answers to that. Thank you very much for your attention. Please feel free to share and like this video. And if you have any questions, as always, please feel free to contact me or my colleagues at ECOROLL AG.